This is section 5.3, day 2, and we are still looking at the definite integral and the concept of area. And sometimes they mean the same thing, sometimes they don't. We're going to talk a little bit about this. And so what we're looking at for our essential question here is we're going to use the definite integral. And so how do we use that definite integral to explore the meaning of the average value of a function? Is our essential question for today. So let's talk a little bit about an average value. The average value of a function is a constant value. And by the definition we're going to use, it's going to yield a rectangular region having the same area and the same width as the region under the actual function. So for instance, if here's a function y equals half x squared, and we go out from 0 to 3, then we can have that region between the function and the x-axis. And the value of that definite integral then, we can put a math 9 into our calculator. Here's our half x squared from 0 to 3, our dummy variable dx. And that answer then is, and then this is the syntax for the older calculators. It'd be, again, a math 9. And here's our half x squared, there's our integrand or our function. There's a dummy variable x, comma, lower bound 0, upper bound 3, close your brackets. These commas can be found on your calculator just above the 7 key. And we get an answer 4.5. So we know the value of this definite integral is 4.5. So let's look at this definition of an average value then. So to find the average value, it's the average value of a function. So the average value then is a y value, and it's constant. And it yields a rectangular region that has the same area, so 4.5 in this case, and the same width, so the width is 3, as what we see under the actual function. So if our average value then is going to be the same value of the integrand divided by 3. So we have then, we must have an average value or a y value for the constant function, a y value for the constant function of 1.5. So if we draw this rectangle here, 1.5 tall, 3 wide, that also has an area of 4.5. So 1.5 is the average value of this function between 0 and 3. Meaning that I should be able to take all of this area above the average value, and I should be able to dice it up and stick it all in here into this kind of little pocket where we have nothing right now. So, so here's the definition then of our average value. Our average value is the integral value, so the value of the definite integral divided by the width. So here's our definite integral notation, and then here's the width. B minus a just means like 3 minus a 0. So, so that being the case, then here's another definition card for the average value, and so we call this the mean value theorem for definite integrals. So again, average value. You know the word average and the word mean the same thing mathematically. So we have, and so we can go on to say that we have the mean value theorem. It says at some location, the actual value of the function will be equal to the average value. So in other words, if we look at this function here, at some location, the actual value of the function will be equal to the mean value. So in other words, somewhere in this domain, b minus a, the actual function and the average value should cross, because that average value is that middle value. And then that's got to occur at least at one location. As long as we have a continuous function, it's got to happen at least once. Our average value or our mean value is going to have to cross once. It's going to have to be somewhere between the smallest and the highest value. And so this is the other thing, is that we already have a mean value theorem for derivatives. And so I personally like to call this the average value theorem for integrals. so that when we talk about the average value, you know we're integrating, and when we talk about the mean value, you know we're differentiating. Okay, so let's talk about average value, no calculator style. So I don't want to use my Math 9 key. So if I can't use my Math 9 key, I better have functions that yield geometric shapes. So for instance, let's find the average value of this function between 0 and 4. So we're going to go from 0 to 4, and we're going to then do the definite integral of this function here, half x plus 4. And that's going to be the value of our definite integral. And then we're going to divide it by the width, which is 4 minus 0. And so, you know, we could do a Math 9 on this, but I want this to be a no calculator style, so we have to rely on our other strategies. And so the strategy we're going to do is we're going to use geometry to calculate the area of this geometric shape. It's all above the axis. It's all in the positive y's, so we know we have a positive value here for this region. So I'm going to split this up into rectangle plus triangle. So the rectangle, the bottom portion here is 2 high and 4 wide. That's going to be 8. This triangle up here is 4 wide and 2 high, and it's a triangle, so it's half that, so it's going to be 4. And so our total value from 0 to 4 is 12. And then if I divide this by the width of the interval 4, what this is saying is I want the top number is saying give me a rectangle with area 12, and the bottom number is saying with the width equal to 4. That means the height has to be equal to 3. So I need a rectangle here with height 3 and width 4, and that's going to have the same area as that purple trapezoid. So if you notice, that average value of 3 yields a rectangle, and I could take this purple slice and stick it into here to fill up that rectangle. Okay, so the average value is 3. You notice that it crosses the function exactly 1 time right here. You can probably eyeball where that happens, but let's go ahead and calculate that mathematically. So where does it cross? It crosses where the function equals the height of the value of that average value, or the height of the rectangle. So it's where the function equals 3. So I'll take the 4 to the other side, and I'll multiply by a -2, and that gets me an x value of 2. So the average value is 3. It occurs when x equals 2. Let's take a look at this example. This is an absolute value, and I want to calculate the average value when I integrate this function from 0 to 5. Okay, so I'm going to integrate that function from 0 to 5, and then I'm going to divide by the width of the domain, which is 5. Now, we almost never integrate absolute value functions. Okay, so this has got to be a geometric problem. So we look at what we have then, and this is getting into what the definition of a definite integral means. So in this case, a definite integral, we know it's trapping a region between a function and the x-axis. So from 0 to 1, that would be this region, and that region is being up in the positive y's is going to have a value of 2 times 1 times a half, which is 1. And then this region, notice I'm capturing it between the function and the horizontal axis. That's the definition of a definite integral. And also a triangle with base of 1, 2, 3, a base of 3, and a height of 3. So 3 times 3 is 9, times a half is 4.5. This is down in the negative y's, so the value of this definite integral is a negative 4.5. And then this last region looks like the first region, also a value of 1. And so the value of our definite integral then from 0 all the way out to 5 is going to be 1 minus 4.5 plus 1, which is going to be a negative 2.5. And then I'm going to divide it by 5. And that negative 2.5 divided by 5 is negative 0.5. So this is saying that I have, again, these two numbers here. This number is the value of the definite integral. So we can see that the definite integral, we have to incorporate the fact that there are negative regions for this definite integral, and we have, in fact, we have much more space below the axis than above the axis. That's why our average value is beneath the axis here. And so we have a definite integral of negative 2.5. We have a width of 0.5. That means we need a rectangle height of downward negative 0.5. So this rectangle then looks like that. And so that average value is negative 0.5. And if you notice, this average value crosses this function in 2 locations. Okay. And so where are those 2 locations? At this point, we would need to graph this on our calculator and graph this value, negative 0.5, and we would need to do a math 9 on that. Excuse me, not a math 9, a second calc intersect on that. And we're going to get to that point of doing that, but we're going to look at different functions before we look at this absolute value function. So we're not going to find these x values, but if I had to estimate, it looks like they might be like a little more than 1, maybe 1 1/4, and a little less than 4, maybe 3 3/4 or something like that. Okay, so here's a calculator style question. Here's a function, and I want to calculate the average value from 0 to 4. So from 0 to 4. So from 0 to 4 gives us this region here, and then this region down here. So we're going from 0 to 4 of 3x minus x squared, and then our width of our interval is 4. So this is a math 9. We're going to go ahead, this is a curved shape. We don't have a geometric formula for it. So when we do a math 9 here, okay, we're going to get the value of this positive region and this negative region all together. And notice the positive region is much larger. So when we do a math 9, we're going to get a value that is positive. And then we're going to divide it by 4. So doing the math 9 gets us 2.667. Again, you have to recognize this on your calculator as 2 2/3. And when we divide 2 2/3 by 4, we get 0.6 repeating, so you have to look at this as 2/3. And so we have a rectangle height of 2/3, and there's our average value. And so notice that this average value also intersects the function in 2 spots. So what that's saying is that, again, we have to take this function and set it equal to 2/3 to figure out where those points of intersection are. And so we're going to do that one. And so we're going to go ahead and show you what that looks like. So I graphed the parabola 3x minus x squared, and I graphed the horizontal line 2/3. And I'm going to go ahead and similar to the parameters I have here. So from 0 to 4 and from minus 4 to 2, 0 to 4, and I went minus 5 to positive 5. And I set my scale at 1, so I have tick marks every 1. And so there are the 2 points of intersection. And then as I do a second calc, I'm going to do an intersect. So that's option 5. And then I'm going to look down here for instructions. My first curve, it's asking me, I'm going to go ahead and I'm going to get close to this intersection, but I don't really have to. But I'm going to now. So the first curve is traveling along the blue curve. It's asking me to confirm the first curve. So I'm confirming the blue curve by hitting enter. And see how it jumps to the red curve? Now it's asking me to confirm the second curve, so I'm going to hit enter again. And that's asking me for a guess, which means I want to arrow close to this intersection and hit enter. And so here is the actual intersection. So the x-coordinate is 0.242, correctly rounded to 3 decimal places per the AP standards. Now I'm going to go back and do intersect again. And this time I'm going to get this intersection. So I'm going to arrow to the right until I get close to this intersection. I'm going to repeat my steps. So notice down here it's asking me to confirm the first curve again. So I'm traveling right now along the parabola. And as I get a little closer to that right intersection, I'm going to go ahead and confirm the first curve by pressing enter right here. Okay, so I'm about close enough to the intersection. Now I'm going to go ahead and I'm on that blue curve, so I'm going to confirm the first curve by hitting enter. It's going to jump here to the second curve, and I'm going to confirm the second curve by hitting enter again. And then I'm going to guess by just getting a little bit closer to the intersection, confirm the guess by hitting enter. And this next intersection is at 2.758, three decimal places to the right of the decimal, correctly rounded. So those are my two points of intersection. And so those are my two locations where the average value and the function value are the same. And it's starting again. There we go. So so here is a different type of problem. So this is kind of getting at the difference between area and average value, or the value of the integral. The value of the integral has positive and negative regions depending upon where the function value lies. Positive regions when it's lying up here above the y-axis, negative regions when it's lying below the y-axis. But if we want to just talk about area in general, as in geometry, as in always positive, then we can talk about the area of a region. So for instance, let's take this whole green region. Well, we need to break it apart into shapes that we can either use a Math 9 on or use geometry on. So for instance, from 0 to 3, that's a curved shape. It's enclosed from 0 to 3. I should be able to do a Math 9 on that and get a value. So when I do a Math 9 in my calculator, I get 4.5. Down here is a rectangular shape. And we don't have an integration we can do in our calculator per se, but we do know that it's 3 wide by 4 tall, so it's 12. And since we're talking about area, even though it's below the axis, I'm going to call it a positive 12 because I'm talking about area. And then this leftover green sliver, which is that, is a little different story because we have to relate it back to calculus somehow. And it's got a curved edge here, which means it's not a triangle. Okay, but we have to take a look at this overall rectangle. So the overall rectangle has an area of 1, 2, 3, 4. It's 1 wide and 4 tall. But I'm not using a part of it. I'm not using this part that's between the function and the x-axis. But I can find the value of that part if I integrate from 3 to 4, the function 3x squared, 3x minus x squared. And so when I do a Math 9 on that, I get a negative value because this portion of the function is underneath the y-axis. I get a negative 1.83 repeating. So the area, the white region there, has got to be a positive 1.83. So as a result, the green area then is 4 minus 1.83 because the green area is just a portion of this whole rectangle. So the green area ends up being 2.167. So to find the total area then, we're going to take the red part, 4.5, and the blue part, 12, and the green part, 2.167, add them all together, and we're going to get 18.667 for the total area of this irregularly shaped figure. So, so we're talking about the definite integral and what strategies can be used to evaluate, I think it's the average value. So we want to graph the function or graph the integrand. We want to use an area strategy if it's geometric. We use a negative area strategy if you have symmetry. And then we want to use your calculator to, if you have neither symmetry nor geometric qualities to your graph. So at this point, you should be able to do 5.3 day 2 homework and also finish up 5.3 day 1.